time. Well, I would say 40% of you. So you will have extra raki tonight. We will begin by the first real Pitch Me Up session. Now you know the deal. 10 minutes, one question, and we skip to the other pitch. And I'm really glad to welcome 1ruthsmitch from SINTEF that has been ranked abstract number 1 over the selection, which is quite impressive vote. Always delivering a vote, always delivering. And just a little change, which is important in the program. I miss Elena Beisel in the program. She will give her talk at the end of the session, just before the invited talk. She will give a talk on innovative nanoformulation of antimicrobial peptides. But now it's time for Ruth. Thank you very much. You have 10 minutes, Ruth.
Thank you very much, Alexander, and thank you to the organizers to give me the opportunity to tell you about our project in the area of ultrasound-enhanced drug delivery. Our vision is to increase cancer survival by improved and targeted drug delivery by developing and implementing an innovative site-focused treatment concept and drug delivery system for solid cancers and brain diseases. What are the medical issues we are trying to address? Everybody knows the EPR effect, and most of the nanomedicine concepts are based on the EPR effect, but we know that this, although the most important concept in modern drug delivery, is not as reliable as previously thought. It's promising in preclinical studies, but then often fails in the clinic. So we need to think out of the box. We need solutions for a post-EPR world. And so we develop a novel treatment concept for cancers, especially solid tumors, where we can enhance or bypass the EPR effect. At the same time, our treatment concept also can be applied to delivery to the brain by transiently opening the BBB. Primarily, the clinical indications will be inoperable solid cancers with low survival rate and where the EPR effect is not reliable and where there are few novel drugs or treatments in the pipeline. And another clinical indication are primary brain tumors and brain metastases. What are the current solutions? The current solutions for cancer, everybody knows: surgery, chemotherapy, radiation, laser and photodynamic therapy, immunotherapy, and hormonal therapy. More than 50% of the patients are treated with chemotherapy, and chemotherapy often has a variable outcome for the patients because low amounts of the drug accumulate really in the tumor, and when they accumulate heterogeneously distributed, and so there are severe side effects and high toxicity. When we look at the ultrasound-mediated drug delivery, what are the current solutions? At the moment, a few clinical trials have started to administer microbubble formulations that are designed for ultrasound diagnostics, to administer them together with systemically administered drugs and then use focused ultrasound. Our solution is an innovative drug delivery system that allows controlled and enhanced delivery of anti-cancer agents to tumors with the aid of focused ultrasound. And our system is composed of 3 elements: nanoparticles, gas microbubbles, and ultrasound. So we have the nanoparticles, and the nanoparticles can be loaded with drugs. They can also be loaded with a fluorescent probe if we want to have. And those nanoparticles are then used to stabilize gas microbubbles. So our gas microbubbles don't have a thin layer of a lipid or a protein like the ultrasound contrast agents, but they are stabilized by a nanoparticle shell, and they look that way in the scanning electron microscope. Those microbubbles can then be used in an acoustic field if we, at a focused place, apply an acoustic field, those microbubbles start to oscillate. And this induces then sonoporation. So we can see that in the area of the ultrasound field, we induce sonoporation, so we induce an artificial EPR effect. And because we have nanoparticles and we also have the microbubbles with a lot of nanoparticles in their shell, we can then change the acoustic field, and in this way we can make the bubbles to oscillate so much that they collapse and they release their nanoparticles. So we get a very high concentration of nanoparticles. At the same time, we get shear stress and a jet stream, which pushes the nanoparticle deep into the tissue surrounding the blood vessels. And also, with an acoustic field, you always get heat. So we have several effects that help us to get the nanoparticles out of the bloodstream into the tumor at a focused place and quite deep. What's the unique selling proposition? At the moment, there is no such product on the market. So we fill a void. That's one of the propositions. What we have is a multifunctionality in one simple formulation. We have an all-in-one product. And our product is prepared by one-step processes for the nanoparticles and the one-step process for the microbubbles. Those processes are easy, cost-efficient, and scalable, and very reproducible. We have made many, many batches and get the same result every time. The system is simple, but it's versatile because we can load the drugs, one or two, in the nanoparticles. We can also use different types of nanoparticles. We get the product with high stability, with high drug load, and a long shelf life. And our product is suitable both for in vivo contrast enhanced US imaging, but also for image-guided drug delivery. Because we have a combination of free and microbubble-associated nanoparticles in our product, we have, by microbubble destruction, a very high local nanoparticle concentration, and by that a high drug concentration in the tissue. And also very important, state-of-the-art ultrasound equipment in the hospitals can be used with minor adaptations, so we don't need expensive investments for this technology. I show you some examples of proof of concept. First here you can see the same batch after preparation and after 8 months, so there's a long-term shelf stability. Also, in animal research, we could see that the mice, they didn't lose any weight. So we have low in vivo toxicity. I don't show any in vitro toxicity results, but I can tell you we have a lot of results there. If we look at the in vivo distribution, these are tumor slices after treatment without ultrasound. You can see a few spots of nanoparticles, green, around the red blood vessels. With ultrasound, you can see a tremendously higher amount of nanoparticles and quite deep away from the blood vessels. About 250 times more drug in the area could we measure. But most important is the in vivo experiment, the efficacy in vivo. We have 3 groups of mice, and we have a breast cancer model. We have a control group, the blue one, where the tumor is growing all the time. Then we have a group which has got the nanoparticle microbubble system, but no ultrasound, and the green one is with ultrasound. And you can see 2 treatments after 21 and 29 days, and you can see a tremendous effect of the total system with ultrasound. And I can tell you now we are at about day 45. We have to sacrifice the control group now because the tumor is too big. The other 2 groups, they are still very okay. Another example that's very difficult to see for you, I think, but this shows an MRI contrast agent in a brain. This is a brain, and only on one side we used our system with focused ultrasound. This contrast agent doesn't normally go through the BBB, but we can clearly see that on one side we have the contrast agent, we don't have anything on the other side, so we open the BBB transiently, and I can tell you there's no bleeding in the brain, and it's closing again. We can show that after a certain time, there's no new contrast agent going through the BBB. So what are the next steps? We are in the process to select specific clinical indications and develop tailored products. And when we have our first product, we will apply to ENCL or to TAB. And we are also in the process to continue and build an IP portfolio and develop a business plan. And that's also why I'm not going into detail to you today, because we haven't secured everything. Thank you very much.
That was a pedagogical session, in fact. That was a correction, right? That was perfect. Okay.
I used your template.
Yeah, thank you. Thank you. One question? Yeah.
Is the effect on the vessels themselves with ultrasound transient, which you see in modeling of the vessel? I mean, in order for them to get through, penetrate through the vascularization, I assume you had an effect on the vessels, on the tumor vessels themselves. If that's permanent or transient.
That I don't know, but the fact that it's transient in the blood-brain barrier where you can easily measure it, I mean, it's very difficult. How do you want to measure whether it's transient in the tumor or not? Yeah, I think the fact that it's transient in the BBB, it indicates that it may be transient also in the tumor. But I don't know.
Thank you again, Ruth. So we go to the second talk, which will be given by Olga Kamona from the team of